A polynomial can be thought of as simply a special kind of mathematical expression. These are all polynomials. This is a polynomial in x, this is a polynomial in x, this is a polynomial in x and y. The peculiar thing about polynomials is the structure of each term. Each term has the structure ax to the k power, where a is any real number and k is either 0 or a positive integer exponent. Now the x is just standing in for a variable, and it could be two letters here as we see in this polynomial. But at any rate, it's this kind of structure for each of the terms. Now the degree of a term corresponds with the exponent on a variable. That is, here this is a first degree term, this is a second degree term. This is a first degree term because of the understood 1. The degree of this term is the sum of the two exponents. It would be a fourth degree term. The degree of this term is 1 and 1, 2. Now we could think of the constants as having degree 0 because after all we could think of something like x to the 0 power here being associated with that term. Now, the polynomial has degree as well. This is a second degree polynomial because the term of highest degree is 2. This is the term of highest degree, and it's a second degree term, so it's a second degree polynomial. Coefficient refers to the number part in a term. The coefficient in this term is 5, the coefficient here 3, the coefficient here -4, the coefficient here 5, the coefficient here is 2. Now, there is a standard form for writing polynomials. We generally write the term of highest degree first, and then the next degreed term, and so on down to the constant term. These are all in standard form. Now, when polynomials are in standard form like this, the leading coefficient, or the first coefficient that we see, will be the coefficient of the highest degree term, and it's often called the leading coefficient. So the leading coefficient here is 3, the leading coefficient here 2, the leading coefficient here 5. There are certain categories for polynomials according to the number of terms that they have. A polynomial with one term is called a monomial. If it has two terms, it's a binomial, and 3 terms, a trinomial. Other than that, they are simply generally polynomials. And in fact, monomials, binomials, and trinomials are also just polynomials as well. Suppose we want to write this polynomial in standard form. We would write the term of highest degree first. We would look through and see that this is the largest exponent on a variable, and so we would write the -5 x to the 7th as the leading term, and then the term of next degree, let's see, that would be this one, and then the 3x, and then the constant -2. So this is a 7th degree polynomial, and the leading coefficient is -5. We're going to go through a number of operations on polynomials now. Once again, this is just a review, I'm sure, but we're going to talk about adding, subtracting, multiplying, and dividing polynomials right quick. To add polynomials, or to add the terms within a polynomial, we're just looking at like terms, and like terms are terms that have the same letters, and those letters have the same exponents on them, and to bring them together, we just bring together coefficients. So here we have a couple of like terms. We're adding these two monomials, you see, and we identified them as like terms because they both involve x and y. The x is squared in both of them, and y is to the first degree. Now, to bring them together, we have -3 of these things plus 5 of those things. -3 plus 5 is 2, so we have 2x squared y for the collection of them. Here we're subtracting a couple of polynomials. This is a trinomial. We're subtracting that trinomial. In order to complete the calculation, we need to burn a step here. We always need to write another step that allows us to drop the parenthesis. It's really important to do that, especially when you're subtracting, because the subtraction here says that we're changing all of these signs in order to collect with the terms over here. And we can think of it as minus understood 1 times every one of these terms in order to complete that sign change operation. So all I've done is drop the parenthesis here and bring these down because the understood coefficient here is 1. That's one way to look at it. And here, minus 1 times all of these, the signs change. This becomes minus 3x to the 4th plus 4x squared minus 3x. And now I want to collect like terms. Now you look around for like terms, and you could reassociate in the problem to put the terms of the same degree next to one another if you want to, but really day to day we're probably not going to do that. When you identify like terms, though, I think it's helpful to do this, is just underline a couple of terms that are alike. That calls your attention to them right quick. 7 of these things minus 3, that would leave 4x to the 4th, and you write that down. And now you're finished with those. You could X them out if you want to, or you could go to the next term or the next group of like terms, and that would be, let's see, the x squared terms are alike. I'll put a different kind of underline under them. And I have minus 1 of these, plus 4 of those. Together we have plus 3x squared. Now we look for any other group of like terms. Well, I don't see another constant term other than this one, and I don't see another first degree term other than this one. So we just bring those terms down. We bring down the minus 3x, bring down the constant, and we're done. To multiply polynomials, the concept is that we are taking every term in one polynomial and multiplying times every term in the other polynomial. And if you just understand that idea, then there are many, many different methods that will work just fine. You probably learned the FOIL method at some point in time earlier. The FOIL method, the idea of first, outer, inner, last. First means first times first. Outer means the outer 2 terms. The inner 2 terms for the I and the L means the last 2 terms. So that accomplishes what we're after here in multiplying every term here times every term over there. I kind of like to do this. Just pick on one term here and multiply times every one of those. And then pick on the next one and multiply times every one of those. And then if you have a trinomial times a trinomial, you use that strategy and it comes out just great. At any rate, it looks like this. 3x times 5x, 15x squared. Then 3x times 7, 21x. Then this term times each of those. Minus 2 times 5x, minus 10x. And then minus 2 times 7, minus 14. And now it's often the case when you multiply a couple of binomials that you have some collection. Those 2 terms are alike. We bring down this 15x squared, collect 21x minus 10x, we have 11x, and then bring down minus 14, and this is our answer. Another arrangement of the 2 binomials for multiplication is a vertical arrangement. We don't often use this, but I just want to make you aware that it's possible. We could arrange them vertically like this and multiply, let's see, 7 times negative 2, that's negative 14, and then 7 times 3x is 21x. Then 5x times negative 2 is minus 10x. Now notice how I'm putting the minus 10x under the 5x, and it also accomplishes the idea of having these terms of the same degree kind of line up for collection a little bit later. Then 5x times 3x is 15x squared. Then I draw the line and collect. This is very similar to the idea of multiplication in arithmetic, and this idea of readjusting the digits, you see, allows us to have digits of the same value added in various columns. So we're accomplishing the same idea here. At any rate, 15x squared, then collecting these 2, we get our 11x, and then minus 14 for the final answer. Recall that when we multiply the sum of 2 terms times the difference of the same 2 terms, the middle term sort of goes out and we get the difference of squares. Here's the long version of that. X times x is x squared, then x times 5, 5x, and minus 5 times x, minus 5x, then minus 5 times 5 is minus 25. And we end up with x squared, and these terms go out, then minus 25. And the fast way to do this is that when we see the sum times the difference of the same 2 terms, we can just say we get the difference of 2 squares. So it's the first term squared minus the second term squared. You see, and that's all there is to it. So when we bump into a problem like this, we recognize it as sum times difference of the same 2 terms, and we can think more in this way than the other way. You see, it's the first term squared minus the second term squared, and evaluate it sort of like this. So we have 49x squared minus 16. Here we're squaring, and notice we have the sum of 2 terms squared. Now it turns out that sum and difference behave in pretty much the same way. But we want to examine the fast way of squaring a binomial here. Now, I'm taking the long route right here. We have two factors of x plus 3, and we use the FOIL method to multiply. But notice that these two terms are exactly the same. So we have two of those things here, and I'm emphasizing it here with this step. And this thing that we have two of is nothing more than the product of those two. So the middle term turns out to be double the product of these two. And the first term is the first term squared, the last term is the last term squared. The middle term is just double the product of the two. Now we can use that idea to deal with a problem like this. Now we're squaring a binomial, so we recall this kind of pattern, and it's a pattern where we think, well, the first term is going to be squared. The next term is double the product of those two. So it's 2 times 4x times 7. And then the last term is the last term squared, and that's all there is to it. And then we perform the indicated operations to get it all of the terms. Squaring here, we get 16x squared. And then let's see, 2 times 4, 8 times 7, 56. X, and then 7 squared, 49. And when we have the difference of two terms, all squared, it's the same idea. It is that, let's see, we're squaring, so the first term of our answer is going to be this first term, all squared. The middle term is going to be just double the product of these two, so it's double 5x times negative 9. And then the last term is the last term squared. Now, it doesn't matter whether we put a plus or a minus in here. For with the 9, when we square, we're going to get a positive result. So let's see, we're squaring here, we get 25x squared. Then the middle term is going to be negative because one of these factors is negative. And then 2 times 5, 10 times 9, 90x. And then 9 squared, 81. Take a look at this pattern. Here we're cubing a binomial. Now, I'm going to use A and B here rather than a number and a letter because we just want to notice a pattern here. A plus B cubed means we have 3 factors of A plus B, so I can list them like this, and then I can just expand as we normally would. Using the FOIL method on these two, I get this, A squared plus 2AB plus B squared. Using the FAST method, you see it would be the first term squared plus double the product of the two, and then plus the last term squared. Okay. Now, I'm just multiplying each of these two terms times every term over here. So A times all of that would be these 3 terms. B times all of that last 3 terms. Let's bring together the like terms. We only have one A cubed term. Then we have a term that is A squared B. You see this contains A squared B. This one contains A squared B. Collecting coefficients, 2 plus understood 1 would give us 3 of these A squared B terms. And then in a similar way, we only have one term of AB squared, or excuse me, we have one AB squared here. We have 2 AB squared here. So together we have 3 AB squared. And then we bring down the B cubed. Now here's the pattern we want to recognize. Think about A and B as just items that fill positions within our original problem. So this is nothing more than the first entry up there cubed. This is 3 times the first entry squared times the second entry to the first degree. This is 3 times the first entry up there in the binomial times the second entry squared. And this is the second entry cubed. If we recognize this pattern, if we use this pattern, then we can very quickly deal with something like, oh, let's say, x plus 5 cubed. Let's go with the pattern now. It's the first entry cubed. Then there is a sort of a naturally occurring coefficient 3. And then there is the first entry squared as an additional factor. And then another factor is one factor of this second entry. So we have a 5 here. And then we have the naturally occurring coefficient 3. And then A, the first entry, that's x in this case. And then the second entry is squared. You see, that's the idea. That's the replacement idea. Sometimes you can do this mentally very, very quickly once you become accustomed to it. And then the last term is the second entry cubed. So now we'll go through and evaluate just a little bit. We have x cubed, And then we have 5 times 3, that's 15x squared. And then 25 times 3, 75x. And then 125 as the final answer. Let's go through it again, and let's complicate things a little bit more. We have 3x minus 2 all cubed. So with this idea, let's see, the first term is going to be the first term here cubed. The second term has sort of a natural coefficient 3, and then we have the first term squared and the second term to the first degree. Now notice the appearance here of this negative sign. That's okay, it'll just jam in here with these factors and we'll end up with a condition of alternating sign, but it's really no big deal. All right, then in the next one we have this naturally occurring 3, and then we have 3x, the first term, to the first degree, and then our second term squared. And then our last term is the second term cubed. All right, let's go back through and evaluate a bit. Cubing here, we're cubing 3 to get 27, and then x is cubed. Now let's see, can we do all of these at one time? Maybe we can. We're squaring the 3 to give 9. 9 times 3 is 27, times minus 2. That's minus 54 x squared. And then in this one, let's see, we're squaring the negative 2. That gives 4. 4 times 3, 12, times 3, 36. So we have 36 x. And then here we're cubing the negative 2, and that's minus 8. Now, notice the alternating sign pattern, plus, minus, when we have a difference that's being cubed. Factoring polynomials can be thought of as undoing the multiplication of polynomials, because what we're trying to do is rewrite a polynomial as a product of 2 or more polynomials. Now you may recall in this process you look first for a common monomial factor, and then after you look for a common monomial factor you look at the number of terms that you have to decide how to go about the factorization. Let's talk about the common monomial factor first of all. In these two terms we look at the numbers and the letters sort of separately and we decide what our common factor is. Well, in the 6 and the 4, 2 is a common factor. And between the x cubed and the x is a common factor. X is common to both terms, or both terms have as a common a common literal factor, 1 factor of x. So 2x is common to both terms. And we pull 2x out of this term, leaving 3x squared. We pull 2x out of this term, leaving minus 2. Now notice when the x comes out of that term, no x factors remain. No letters at all remain. We just have the minus 2. The one really nice thing about factoring is that you can always check to see if you have the answer correctly or if you have a correct factored form. And you check just by multiplying out the factors that you have listed. So is it the case then that 2x times this binomial will give us what we started with? And in examining that and seeing that we do have this, the product of these two will be that, then we do have a correct factored form. All right, here we have 3 terms involved. We're looking for a common factor. We can pull 4 out of all 3 of these terms. There's no letter that's common to all 3. These 2 terms have x's involved with them. This one doesn't. So there's no common letter factor. But 4 is a common numerical factor in all 3 terms. And so we could factor 4 out of them. We could also factor negative 4 out of them, and factoring a negative will serve the purpose of changing all of the signs in the polynomial that we start with. Let me show you what I'm talking about. When I pull negative 4 out of this term, I'm left with x squared. Negative 4 out of this term leaves negative 3x. And negative 4 out of this term leaves plus 4. So notice how the signs have changed. The first term here from minus to plus, plus to minus, minus to plus. A lot of times that technique of factoring a minus or a negative out of a polynomial is necessary to complete a certain form. All right, here we have a situation where the common factor turns out to be a binomial. Now the 2 terms here that are being factored are these 2 terms. And these 2 terms happen to have a common binomial factor. And those common factors, that binomial is treated just like a letter would be treated. If this were n times 2x and n times 3, we would know how to take out that common factor of n? Well, we take out the x minus 2 in exactly the same way. So we pull out x minus 2. From this term, we're left with 2x. X minus 2 out of this term leaves plus 3. So here's our factored form. One of the situations involved in factoring and using this idea of looking at the number of terms involved is a situation where we're faced with factoring the difference of squares. Now remember where the difference of two squares can come from. We had before that when multiplying the sum of two terms times the difference of two terms, we get the difference of two squares. So it kind of makes sense that when we're faced with factoring the difference of two squares, they're going to factor into the sum of terms times the difference of two terms. So if we have x squared minus 9, we factor into, let's see, the product of two binomials. One of them has a plus sign in it, the other minus. And we just ask ourselves, what is being squared to give each of the two terms? And we're identifying the items that are in the two binomials. X times x to give x squared, 3 times 3 to give 9, and the signs are different, and we're all done. Now here's a situation where this is not the difference of squares, but we're supposed to look for a common factor when we begin the factoring process. And here we have 3 as a common factor. And when we take the 3 out of this term, we're left with 1. We take 3 out of this term, and we're left with minus 4x squared. Now, once we take out that common factor of 3, we see that here we have the difference of squares. And a lot of times a common factor can mask a certain kind of special factorization process, because we'd be looking for the difference of squares. We don't see it here. We might think it's not available to us, but yet we can see it once we've taken out the common factor. That's the idea. All right, so now that we've taken that common factor out, let's see, we have what squared to give 1? Oh, 1. You see, and then we have plus and minus. And then what squared to give this? Well, think about the numbers and the letters sort of separately, and we find this to be 2x, 2x. Here's one where we also have the difference of squares. The numbers are getting a little bit bigger, and we have an exponent of 4 here on the x. No matter, it's the same idea. We go about the business of identifying the items in the two binomials. Now, what is being squared to give 16x to the 4th? Well, 4x squared, you see, is squared to give 16x to the 4th. So we have plus, minus. For 81, it's 9 times 9. Now, a lot of times there's a tendency to just stop the factoring process once we go through one step, sort of like this. But always check to see if one of the factors that are in an already factored form is factorable even farther. And here we see that. We have the difference of squares right here. Now, we can't factor the sum of two squares, but we can factor the difference of two squares. So we'll take this factor and simply bring it down, and then factor this into the sum of terms times the difference of terms. It's 2x times 2x to give 4x squared, and it's 3 times 3 to give 9. One's plus, one's minus, and we're all done. Here we have a situation where, and I've copied this wrong, this is x minus 2 squared minus y squared, and this is the difference of two squares. It's just that one of the terms being squared happens to be a binomial. But that's no big deal. You're just following through with the same kind of technique that we've been talking about. Pop in a bracket here, I would suggest, and use the same idea that we had before. What's being squared to give this first term? Well, this binomial is squared, you see, and so you list the binomial here in both places, and then it's the plus minus idea, and then y is being squared for this last term, and this is the factored form. We probably would drop the parenthesis within the brackets, and even the brackets can change into parenthesis like this. Oops. So we have x plus 2 plus y, x plus 2 minus y as the factored form. Now, I said that the difference of squares is factorable. The sum of squares is not factorable. There are other binomials that are factorable. The sum and difference of cubes are both factorable, it turns out. Now the factorization, though, is accomplished by sort of a pattern recognition, and it turns out that for both the difference and sum of cubes, the pattern is binomial times trinomial. Now let me just create a little space here. So if we understand that the pattern is binomial times trinomial, we would start with the pattern. Just start with the skeleton of a binomial times a trinomial. And we identify the binomial part first, and then the trinomial part from the binomial part. Okay, for the binomial part, we just identify what's being cubed to give each of these. X is being cubed to give x cubed, 2 is cubed to give 8. And the sign that appears here is the same as this sign, so it's minus. To identify the parts of the trinomial, the first item in the trinomial is this first item in the binomial squared, so it's x squared. The last term is this last term squared. The middle term is the product without regard to sign. And it looks like to me I need a little more room here. Let me just stretch this out a little bit, make it look a little cleaner. Okay, the middle term is the product of these two without regard to sign. So 2 times x, 2x. And the sign turns out to be opposite that sign. If that's minus, this is plus. And if that's plus, this would be minus. Okay, let's go through it again. This time we have the sum of cubes, and once again we have the binomial times trinomial situation. So let's see, for the binomial part, what is cubed to give this? Oh, x. What's cubed to give that? 5. Sign is plus, so plus. First term here is that guy squared. The last term is this one squared. And the middle term is the product of these two without regard to sign. So we have 5 times x, 5x, and the sign is opposite this sign, so it's minus. So here's our factored form. Factoring a trinomial, you may recall that generally speaking, if it is factorable, then it's going to be a binomial times a binomial. And we're sort of using a trial and error method here to complete the factorization. So we think about binomial times binomial, and we remember the FOIL method, and we understand that it's probably the case that this first term, you see, of the trinomial to be factored, particularly if it's in standard form. The term of highest degree is here. So it's the first term here times the first term here to give the first term there. So it's x times x to give x squared. Then we look at the sign pattern. We see that the sign of the last term is positive. So that means that the signs of these two terms have to be the same, plus times plus or minus times minus, to give a positive result. We look at the middle term. Oh, it's negative. That means it's minus times minus. Now, factors of 12 are going to go into these two positions, but there are a lot of ways to factor 12. 12 could be 4 times 3, it could be 6 times 2, it could be 12 times 1. Now we understand that the minus 7x is the collection of this product and this product. So really we are looking for factors of 12 that add to give 7. That's the idea here. We can think all the way through the factorization of a trinomial like this, particularly when we have a leading coefficient of 1. We can easily think through the whole situation. So we have the 4-3 combination, factors of 12 that add to give 7. We can verify the factored form, x times x to give x squared, minus 4 times minus 3 to give 12, minus 4x minus 3x gives minus 7x, a correct factored form. Now, here's one with a leading coefficient that's different from 1. It presents us with more options, I guess, to try in this trial and error process. The factors for 2x squared would presumably be 2x times x. Now, the last sign is negative, so it's a plus-minus combination. And just guess at this. There's no real easy way to determine whether the plus goes here or there. So just take a shot and put something down. Now, factors of 15, probably the 5-3 combination. You might try the 5, we could try the 5 here and the 3 here. We would have 3x minus 10x. 3x minus 10x, that's negative 7x. Gee, that's not it. So that's not right. So the 5-3 combination might go the other way. Let's try 3 here. Whoops. Let's try 3 here. No, excuse me. Let's try 5 here. I had it right the first time. And 3 here. So we have 5x minus 6x. But minus 6x plus 5x is negative 1x, but we want plus 1x. What's wrong with this picture? Well, all we need to do is swap signs, make that a plus, make this a minus, and we should have the right factored form. Let's verify the middle term. Minus 5x plus 6x is plus 1x for the middle term. Correct factored form. Here's another one. This one happens to be a rather special one, but it doesn't look particularly special on the surface. Let's just go through and factor using our sort of trial and error method, x times x to give x squared. Last sign is plus, so these two signs are the same. Middle sign is negative, so it's minus minus. Factors of 25 are probably 5 and 5. Let's verify the middle term. Minus 5x with another minus 5x would give minus 10x. A correct factored form then is what we have here. We notice that we have a couple of binomials times one another. That is, we have the same binomial appearing as a factor twice, and we can indicate that as x minus 5 all squared. Now, this is called a perfect square trinomial because it comes to us as the square of a binomial. So we have a binomial squared giving us a square. So it's a perfect square trinomial. That's why it's called that. Now generally, we could go through and evaluate a lot of trinomials like this and try to identify those trinomials that are perfect square trinomials and go directly to this factored form. But it's really not worth the effort. Using the general method usually works out just as well. In order to identify a perfect square trinomial, understand, you'd have to recognize this is a square. That's easy. This is a square. That's pretty easy. The sign here has to be plus, and this middle term has to be fundamentally the double the product of the two items being squared to give those two. You see, that's the idea. We'd have to recognize all of that to recognize that as a perfect square trinomial. And again, it's not really worth the effort, unless you had about 50 of them to work. Another situation involving factoring is the notion of having 4 terms. Now remember, I mentioned early on that you kind of jump start your logic pattern of factorization by looking at the number of terms involved once you have tried to take out a common monomial factor. Well, the technique that's used when 4 terms are involved is the method of factoring by grouping. Now, factoring by grouping works like this. Now, we would look for a common factor, we don't see one. Then we would group. Put these two together, think of those two together. With these two, we have a common factor of x squared. When I snag out the x squared from this term, I'm left with an x. When I snag x squared out of this term, I'm left with minus 2. Now I shift my thinking over here. 3 is a common factor over here, so I could take out a 3. Now look at what happens if I take plus 3 out of these two terms. If I take 3 out of here, then I have minus x. If I take 3 out of here, then I have plus 2. Now look at these two. Oh, x minus 2 and minus x plus 2. Wow, what can I do to make those look alike so I can factor further? Well, if I can just get these two signs to change, then I'll have the same binomial in both of these terms. And I can accomplish that rather easily. All I needed to do was to, instead of taking out 3 from these two terms, just take negative 3 out of them. So negative 3 out of this term would leave x, and negative 3 out of this would leave minus 2. Now I have x minus 2 in both of these, so I can pull x minus 2 out of each of these terms. X minus 2 out of this term leaves x squared, and x minus 2 out of this term leaves minus 3. So our correct factored form. This, by the way, is not the difference of squares because 3 is not a square. In this one, once again, we have 4 terms. We would look for a common monomial factor. We don't see one, so we would go through the method of factoring by grouping. Now, by the way, you might be thinking, well, gee, why did we group the first 2 terms together? Why not group, for example, x cubed with minus 3x? Those have a common factor, and then these two together. Well, it turns out that way of grouping would work. There's a third way of grouping. We could group x cubed and 6 together, and then these two together. Would that work? Well, it turns out that there are 3 grouping possibilities in problems like this, and 2 of them will work to give a correct factored form, and the third one will not. So, but to resolve the situation, if the polynomial is relatively normal looking, then just write the terms in standard form and group from left to right, and that generally will take care of almost all of the situations. Here, for example, notice we have this in standard form, and so I would just kind of group from left to right, this pair and then that pair, and that's probably the right way it's going to work. All right, for these two I have, let's see, 5 is a common factor of both terms and x squared is in both terms, so I'll pull 5x squared out of these 2 terms. 5x squared out of this term leaves x, 5x squared out of this term leaves minus 2. And for those 2 terms, I see that 3 is a common factor. When I pull 3 out of this term, I'm left with x. 3 out of this term leaves minus 2. And I have x minus 2 as the common factor in these 2 terms. When I pull out x minus 2 from this term, I get 5x squared. When I pull x minus 2 out of this, I get plus 3. So here